900,000 people live atop an ancient caldera that has been steadily rising, over 1 meter in less than 2 decades. Experts assumed rising magma was to blame, until new research from Stanford revealed something more unnerving. Campi Flegrei may be breaking open beneath the seafloor because of pressure from trapped groundwater and vapor in the geothermal reservoir, not lava. If true, this changes how and whether we can prevent disaster. But what evidence uncovered this hidden danger? A vast volcanic depression stretches beneath the western edge of Naples, spanning 11 kilometers from rim to rim. Across this landscape, nearly 900,000 people live and work, densely packed into neighborhoods, apartment blocks, and historic towns that sit directly above the restless caldera. The ground here is anything but stable. Since 2005, precise GPS and satellite measurements have recorded the surface rising by 1.4 meters, more than the height of a kitchen table, across the most active zones. This uplift is not a slow, imperceptible drift. In recent years, the rate has surged to about 15 millimeters per month, enough that cracks appear in roads and walls, and door frames shift out of alignment. The deformation centers on Pozzuoli, a city built atop the northern rim, where the streets and squares now stand higher than at any point in living memory. Urban infrastructure, including schools, hospitals, and rail lines, lies within the caldera's boundaries, with no buffer between daily life and the forces below. The entire metropolitan area, from the port of Naples to the volcanic hills, is interlaced with utilities and transit routes that cross ground in constant motion. Unlike remote volcanoes, Campi Flegrei's hazard is magnified by its human footprint. Every centimeter of uplift adds tension to buildings designed for a static Earth. Each new earthquake, however minor, rattles a population that remembers past evacuations and wonders how much more the ground can rise before something gives. The scale of exposure is unmatched in Europe, a city of nearly 1 million, living atop a restless, swelling caldera with no clear line between normal life and geological risk. In the autumn of 1983, the streets of Pozzuoli emptied almost overnight. Sirens echoed through the city as 40,000 residents packed their belongings and boarded buses, leaving behind shuttered schools, abandoned shops, and homes with cracked walls. The term for what drove this exodus, Bradyseism, entered public vocabulary. A slow, relentless rising and falling of the ground, powered not by a single eruption, but by pressure building deep below. Over 16,000 earthquakes rattled the region during that crisis, some strong enough to collapse ceilings and send masonry tumbling into the streets. Civil protection records from those months describe a city transformed by fear and uncertainty, with families relocated to distant towns and emergency shelters filling with people who had never imagined they would become evacuees in their own country. The 1983 to 1984 Bradyseism left scars deeper than the physical cracks in concrete. For many, the memory of that evacuation still shapes daily life. Older residents recall the sound of tremors at night and the constant updates from the Istituto Nazionale di Geofisica e Volcanologia, known simply as INGV, whose scientists worked around the clock, tracking every tremor and every centimeter of uplift. Their archives hold thousands of pages of handwritten logs, seismic charts, and official bulletins that chronicle not just the science, but the human cost of Bradyseism. The experience forged a culture of vigilance, where even minor tremors prompt unease and official warnings carry the weight of lived experience. The legacy of those years ensures that every new sign of unrest is met with both scientific scrutiny and the collective memory of what it means when the ground beneath an entire city begins to move. For decades, the scientific playbook for Campi Flegrei has centered on magma. The classic warning signs are familiar: earthquakes that start deep below the caldera and migrate upward, subtle changes in the chemistry of volcanic gases, and steady ground uplift. Each of these signals has been used to infer the movement of magma, molten rock rising through the crust, pressurizing the system from beneath. The Istituto Nazionale di Geofisica e Volcanologia, known as INGV, has built its monitoring network around these criteria, tracking seismicity at multiple depths, measuring helium and carbon dioxide ratios in fumaroles, and modeling deformation patterns to estimate the shape and pressure of the underlying magma chamber. Historical episodes, including the lead-up to the Monte Nuovo eruption in 1538 and the seismic crises of the late 20th century, were interpreted through this lens. Deep quakes, followed by accelerating uplift and gas anomalies, meant magma was on the move. The operational stance has been cautious but clear. When these classic indicators align, the risk of eruption is considered elevated. This model has shaped evacuation plans, hazard maps, and public communication for generations, setting the expectation that the story of Campi Flegrei's unrest is, at its core, a story about magma. Stanford researchers led by Xing Tan and Gregory Barroza have brought a new perspective to Campi Flegrei's unrest. Their work centers on a stepwise process that starts not with magma, but with water. Rainfall and surface water gradually seep into the ground, recharging a deep geothermal reservoir 2 to 4 kilometers beneath the caldera. Over time, this influx is trapped by a cape rock, an overlying layer of volcanic rock that laboratory experiments show can self-seal within a day, thanks to rapid mineral fiber growth at high temperatures. With the cap rock sealed, groundwater and vapor accumulate, building up pore pressure in the reservoir. Modeling shows this overpressure can reach several megapascals, enough to deform the rock and push the ground upward, but still well below the point where the cap rock would shatter catastrophically. As pressure rises, it reduces friction along faults, priming them for slip. When the threshold is crossed, brittle failure occurs. Faults slip, earthquakes rattle the surface, and the ground lifts in tandem. This 5-step mechanism, recharge, sealing, pressurization, strain, and failure, matches the observed pattern of uplift in swarms. The team's pore pressure modeling suggests that managing fluid pressure, not just watching magma, could be key to understanding and reducing seismic risk in the caldera. Machine learning has redrawn the seismic map of Campi Flegrei. By analyzing continuous seismic data from 2022 to mid-2025, researchers cataloged 54,000 earthquakes, over 4 times the number detected by traditional methods. This dense swarm of previously hidden events forms a sharp pattern, a ring-shaped fault encircling the area of maximum ground uplift, with its center beneath Pozzuoli. The ring fault geometry, now clearly defined for the first time, aligns precisely with the zones where the ground is rising fastest. 2 major faults converge directly under the city, tracing a structural weakness that had remained obscured until now. Nearly all of these earthquakes are shallow, originating less than 4 kilometers below the surface. This pattern supports the idea that pressure from trapped groundwater and vapor is straining the caldera's upper layers, rather than magma pushing upward from depth. The ring fault's clarity in the new catalog and the clustering of events along its arc provide physical evidence that the caldera's unrest is being driven by fluid pressure along these pre-existing weaknesses. The discovery not only confirms the plausibility of the hydrothermal pressure model, but also raises new questions about how risk might be managed in a city built atop such a complex, reactive fault system. Hydrogeologists and water managers are now considering a practical approach, expanding the network of monitoring wells across the caldera to track real-time changes in groundwater pressure. These wells would serve as sentinels, recording subtle shifts in aquifer levels and pore pressure at various depths. Alongside this, controlled pumping trials are being designed to test whether targeted extraction from overpressured zones could safely lower fluid pressure in the reservoir. Feasibility hinges on detailed hydrogeological surveys, mapping the connectivity between shallow and deep aquifers, and identifying the most responsive locations for intervention. Pilot projects would require a stepwise framework, baseline measurements, gradual pumping, and continuous monitoring for any sign of land subsidence or unintended seismic effects. Each metric, including pressure drop, response time, and ground stability, would help determine if managing groundwater offers a viable path to reducing seismic risk beneath one of Europe's most densely populated volcanic fields. Coordinating a response to Campi Flegrei's unrest demands more than technical fixes. It requires institutions to work in lockstep, sharing data and aligning priorities. Civil protection agencies, water authorities, and research groups must pool resources to fill crucial gaps in knowledge. Decades of rainfall, well and aquifer records, much of it still on paper, need to be digitized and analyzed to reveal long-term patterns linking groundwater changes to seismic activity. Field teams are preparing tracer tests to map how water moves between the surface, shallow aquifers, and the deep geothermal reservoir, essential for understanding connectivity and potential intervention points. Yet even the best models have limits. They depend on assumptions about subsurface pathways and reservoir behavior that may shift with each new earthquake. Replicating results and sharing raw data across agencies will be vital. Officials stress that any move toward intervention must proceed with caution, grounded in evidence and guided by ongoing transparent research. Today, science reveals that water, not just magma, threatens lives above Campi Flegrei. As climate shifts bring heavier rainfall, managing groundwater is not just theory, it is urgent policy. The next move could decide whether this restless caldera remains quiet or reminds Europe why it is called the burning fields. Share your thoughts below.